In the last video, we finished the ball counters and motion controls. Today we'll hit the bricks. I keep thinking this is going to get easier. Not in this town. Also, a quick clarification. Normally we have one module definition per file, with exceptions like TTL and gates. In the ball motion file, we actually have 5 module definitions, a ball motion wrapper at the top, and 4 submodules at the bottom. We then instantiate those 4 submodules within the ball motion wrapper, and in main we're instantiating and wiring everything up, basically in order as we go along. Wires and buses for any output ports are placed directly before the modules used, so it's easy to see who's driving what. Then those wires and buses can be used anywhere within that file. One thing we completely forgot to test last time was the paddle and Y-motion ball deflection angle. We just need to wire PC and PD from the paddle module to the Y-motion control instance. You can check out part 7 for more details, but basically the paddle is broken up into 4 zones. The bottom latch controls whether the ball goes up or down based on PD, and the top latch controls the Y speed. The deflection angle is determined solely by which zone is hit. The inbound angle is completely ignored. I'll disable the small paddle when hitting the back wall, and also prohibit stepping the volley counter so we can more easily capture the deflection angles. Looks like that's all working fine. I backed out all of our temporary crap so we have a clean slate before starting on the bricks. I am going to drop everything in GitHub as soon as we get a little further along, so bear with me. I'll start a new file for the bricks, and we'll need our defines this time. This section takes in the horizontal and vertical UI signals, and we'll also need RAM Player 1. Going down the line, we'll need attract, the FPD lines from the empty wall detector, VSync, those 2 hit lines from the motion controls, ball display, start game, and serve wait from the game state logic, and finally CKBH from the oscillator divider. She then puts out brick display, brick hit, set bricks, and our can hit bricks line, which is used in scoring. This section uses a couple of flip-flops, an SR latch, a bunch of gates, and this 256 by 1-bit static RAM. We've got everything but the RAM, so let's go build one of those. I'll add the 82S16 to our TTL file and add the parameters. The storage itself is easy. We can just make a long register. And we'll set all bits off by making 256 copies of a single 0 bit. Next, I'll make a single chip enable that rises when all 3 CEs go low. Writing is easy. We enter the always block when write enable drops, and if the chip is enabled, we store the data in value into the array. Data out in this chip is an inverted copy of the cell value. We drop the output only if the chip is enabled and the address cell is on. Otherwise, data out stays high. Well, that was pretty simple, but it won't work in this design. Breakout's memory write for hitting individual bricks is fine, but the methods used for filling walls do not comply with either of the datasheet specified write methods, but somehow it still works. There are 2 fill operations for putting up bricks. One is via the set bricks latch, and the other is via the FPD lines. For a set bricks operation, this latch turns on when you press one of the start game buttons. Set bricks then does a few things. It force asserts brick hit, which drops write enable. It forces data in high, and it gates 2 Henry to RAM address able7 through the RAM player 1 line. This continuously cycles through all RAM addresses, turning on all bricks for both players. This cycling continues until serve wait rises after pressing the serve button. An FPD operation, on the other hand, happens when a player completes their first wall and the ball hits the paddle. This triggers their empty wall detector one-shot and asserts their FPD lines. Asserting FPD from either player forces data in high and write enable low. Able7 is determined by the player that's up, so only their bricks are set. Now the only way to clear bricks is to hit them during gameplay. During the entire game, data in is simply held low. CKBH is timed so that the fetched cell data is stable before checking for a collision. If the ball runs into a brick hit is asserted and drops write enable, modifying the cell. Brick hit also resets the can hit bricks latch, which force resets the brick hit latch and raises WE. The right pulse width is therefore determined on how quickly brick hit propagates through this loop to reset itself. So our nice SRAM module won't work for fill operations because we're not pulsing right. To fix this, we could introduce some clock for the always block, then check if WE is low and write the data in value to the selected address. My preferred method is to simply fix the WE line to properly pulse for every write during fill operations. If we look at the timing, we can see that CE asserts during brick time for each horizontal line. During an FPD operation, 7 address lines are changing, and we can use 2 Henry to make decent write pulses. For set bricks, all 8 address lines are switching as they gate 2 Henry through RAM player 1 to able7. Here we can use 1 Henry as a write signal to properly set the addressed cells. We can simplify this a bit by just using 1 Henry for both operations. FPD refills will simply do 2 writes for the same address without harm. I'll use this circuit to generate decent write pulses. We detect a fill operation by checking if set bricks or one of the FPD lines is on and gate 1 Henry to write enable. When not doing a fill operation, brick hit is gated through normally. This is one simple logical change we need to make to properly stuff this into our FPGA. Also with this circuit, we no longer need to force set the brick hit latch, simplifying the wiring here. Well, time to shut up and wire it up. First, add that set bricks latch. Create data in. Consolidate that third enable line. Create a fill signal that's on during a set bricks or FPD operation. Now we can generate a nice write depending on if we're filling or just hitting a brick. Add a loose wire for data out. Add that RAM chip. Assign the output. Add that can hit bricks SR latch. And finally the brick hit latch. I'll make a wire for that line coming off EZ3 dog because it's used in 2 places. Copy that signature to main. We don't have the FPD lines yet, so tie those. We don't have ball display yet, so we'll just use ball. Well, we don't have start game or serve wait either, so I'll just tie those appropriately. Create loose wires for those outputs. Build that. And she pukes. Well, the compiler's telling us we have a logic loop, exactly as we described before, where the brick hit line folds back and modifies itself. This works fine in discrete logic, causing a short spike of brick hit depending on the gate delays. But in the FPGA, it's a bozo no-no because the delays are so short there's no guarantee that the spike will exist or be useful. To remove this loop, we can remove the loop, but we still need some signal to reset the brick hit latch to create a short brick hit pulse. Since CKBH always rises when the clock is high, and clock drops one oscillator cycle later, we can use a clock line to nicely reset this latch. I'll add clock to the module definition, use it for the reset, and wire that up in main. The build is now error-free. Upload that, and no bricks. Oh yeah, there are no bricks because the RAM initialized to all zeros. We can temporarily initialize to all ones and turn that on. And there they are. We haven't connected brick hit to the motion controls yet, so the ball keeps going. Attract mode is hardwired off here, so brick hits work. Let me revert that RAM initialization to 0, then wire button 1 to one of the FPD lines. Then tie button 2 to attract. Turn that on. Simulate FPD, and the bricks show up. Turn off attract mode, and bricks are eaten. Release attract mode, and the bricks stay put. Wire button 1 to start game and button 2 to serve wait. Bricks fill when I hit button 1. Press button 2 to deassert set bricks, and hits work fine. Well, she seems to be working properly. Alright, another fun one. Now that we have a few UI elements on the screen, we need the game state controls to tie it all together. But before we get to that, I'm going to do a short showcase video next. Many viewers have built their own retro boards, and I want to show some of their amazing work. If you rolled your own, ship me some pics or videos so I can show it in a future segment. Thanks for watching.